Chemistry 3202 course overview, Unit 1, Section 1, Lesson 1. Remember, if you want background information on this, you can consult the content link, and you will go to Content, then click on Unit 1, then Section 1, and then Lesson 1, and you will get background information on the collision theory. Oops, Chemistry 3202, there we go. The textbook readings for this section, you can consult the textbook as well as the content. All right, and here are the pages that you can see information regarding the collision theory. And you can also go check some practice problems in the textbook, page 486 and 538. These items relate to the collision theory. Here are the outcomes that are expected for you guys to know in this particular lesson. The kinetic molecular theory, a quick overview here. There's 3 points to the kinetic molecular theory. Number 1, all matter is composed of atoms, ions, or molecules. And this is a basic premise of all chemistry. You have to believe this. Everything that we talk about in chemistry is centered around this particular idea, that all matter is composed of atoms, ions, or molecules. Number 2, the particles are in a state of constant random motion. They're always moving regardless of if they're in a solid, liquid, or the gaseous state. They're always moving. And because they're always moving, they're always colliding and banging into other molecules, atoms, or ions. And what we're saying then is that when they collide with one another, they're going to impart energy as well. So when 2 cars collide on the highway, there's energy exchanged. Or if you're playing pool on a pool table, when the balls on the pool table collide, they impart energy to the other ball, and that's what makes the other ball move. So the molecules are in a state of constant motion, and the energy they have when they collide, they can exchange energy. This can be seen in the pressure inside a balloon. If you blow a balloon up and tie it tight, and then you squeeze the balloon with your hand, what you're doing is feeling the air inside the balloon colliding with the walls of the balloon, and that pressure you feel is the air colliding with your fingertips on the surface of the balloon. Number 3, an increase in the energy of the particles causes an increase in the motion of these particles. So as the particles begin to get heated up, as we heat and heat and heat, the molecules move faster and faster and faster. They're going to require more space to maneuver and move around. And we see this in the expansions of solids and liquids, increased pressures of gases. If we take that balloon that we just blew up and put it in the hot sun, the balloon is going to start to expand and get tighter, the pressure starting to go up because the molecules inside that are getting real excited. They're moving further and faster, and they're expanding and pushing on the sides of the balloon, causing more pressure. Some more observations that we can see in everyday life that can support the kinetic molecular theory. If you have a bottle of pickles and you want to try and get the cover off, okay, warm it under some hot water under the tap, and then that's going to cause the metal cover to expand faster than the glass, and of course it's easy to remove the cover off the bottle of pickles. Another observation, expansion joints in bridge. Every time you go over a bridge in a car, you hear clunk, 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 clunk. If you inspect the bridge, there's metal expansion joints there. There's spaces between each end of the bridge, and that's the space that the bridge is allowed to slide back and forth on, so that in the hot summer weather, when the concrete in the bridge begins to expand, it has a space to spread apart on so that the bridge won't buckle because of the expansion due to the heat. And again, during wintertime when the bridge gets cold, the concrete and the metal starts to contract and get smaller because the concrete particles are moving slower. They're starting to move closer together, and hence it allows the bridge to slide back and forth. So there we go. Another observation we might see is when you have diffusion of gases. Suppose your buddy next door comes in your classroom and they've just freshly put on a bunch of Axe deodorant or some other type of deodorant. It's a very strong deodorant, and it vaporizes and it begins to fill the room with that gaseous Axe or cologne odor. And of course what happens is eventually the cologne begins to fill the room, and that's because the gas molecules are moving to fill their container. So all these observations support the kinetic molecular theory. Now the collision theory builds on this idea, the fact that particles are in a constant state of motion, they're colliding, and if we give them more energy, then we're going to make them move faster, and when they collide, they're going to collide more frequently. So we're going to use the collision theory as a theory of chemical reactions, and there's 3 points to the collision theory. The first point would state that in order for a reaction to occur, the molecules have to collide or come in contact with one another, and that makes sense. You know, you can go with a gallon can of gasoline or a 5-gallon can of gasoline. It doesn't blow up for no reason at all because it's not in contact with the air. The gasoline has to mix with oxygen in order for it to combust. So that's an idea that, okay, yeah, they have to be mixed. We have to mix the things together in order for them to collide with one another. If we have them in separate containers, they're probably never ever going to be able to come in contact. Number two, not only do they have to collide with the proper orientation, they have to collide correctly. All right, they just can't collide together in any old orientation whatsoever because they may just bounce off one another because they may not be in contact with a reactive site. Number three here, in case you're wondering, that's the bell going off in my school. All right, well, I'm not on a submarine. Okay, number three, the particles have to collide with sufficient intensity. They have to have enough energy to cause the old bonds to break and the new bonds to form. If they're just really, really slow, if it's a really cold temperature and the molecules are simply rubbing one another and bouncing off, that may not be enough energy to cause a chemical reaction. You know, so it has to be at a specific intensity. The molecules have to collide hard enough in order to break these old bonds. Okay, and another idea says, okay, well, one of these alone is not sufficient for a chemical reaction to occur. All three conditions must be met in order for a chemical reaction to occur. And that's what we're seeing. Now, you guys have witnessed something like this in Chemistry 2202. If you look at something like an esterification reaction where we take, say, a carboxylic acid and an alcohol react to form an ester. Okay, now the reactive sites on these two molecules is going to be the O group on the alcohol and this particular C in the carboxylic acid. So that if these molecules collide like that, if they bump together like that, nothing's probably going to happen because that's not the correct orientation. What's going to have to happen here, I'm going to put my hydrogen back there, what's going to have to happen here, of course, is that this hydrogen, this alcohol is going to have to come underneath here and rotate a bit so that we get the collision in the proper orientation. So this oxygen is somehow going to have to collide right there. It's no good for it to collide here with that C. It has to collide with this C. So this idea of orientation, we have to have the molecules arranged in the correct angles and everything has to be perfect in order to get a chemical reaction to occur. There we go. So all three must be met. The rates of chemical reactions can be measured here as well. We want to be able to measure how fast the reaction, if a reaction is going to be successful, if all three conditions of the collision theory are met, we want to be able to measure how fast the chemical reaction is. So the rate of a chemical reaction is the rate at which products are produced, or we could measure the rate at which reactants are consumed per a unit given time. So how much is consumed per second, how much is produced per minute, things along that line. So if we're going to measure a rate of a reaction, the more successful the collisions are, if the collisions have enough energy and they're the correct orientation and they're colliding frequently, the more they have, then the faster the reaction rate is going to be. So we should measure a quicker change in reactants or products. Now some of the things we can measure here if we're measuring the change in rate over time could be the change in mass if it's a solid. If it's an acid or a base that's present in a chemical reaction, we can measure the change in pH over time by using a pH meter. We could measure the electrical conductivity over time if the reaction involves ions. If the reaction involves gases, we can measure the change in pressure over time. If a reaction involves a change in color, like from colorless to orange or from blue to colorless or something like that, we can actually measure the change in color over time by using a device called a colorimeter. And also if we have gases produced, we can also measure the change in gas volume over time. And what we're saying here is we can easily measure the rate of a chemical reaction, because if we were measuring volume, and let's say we collect 15 milliliters of gas in 90 seconds, then we could easily calculate the rate of that chemical reaction. It would be 0.167 milliliters of gas produced per second. All right, so in that way we could quantify the rate of that chemical reaction. Now you guys probably did a lab on this, and the lab on this, where we would measure reaction rates, we took something like sodium bicarbonate and we reacted it with hydrochloric acid. And what we're seeing here is that this reaction is going to produce carbon dioxide gas. So in the lab, you guys would have measured this by taking something like an Erlenmeyer flask and taking a rubber stopper with a hole in it with a tube, and you'd have an upside down container here that would be filled with water. And as this chemical reaction started, so the sodium bicarbonate reacting with the hydrochloric acid would produce carbon dioxide. The carbon dioxide would move up to this tube and would go under the water and start bubbling out and displacing the water in this container. So you would measure, you knew that this container was filled with water, and as the bubbles were produced, you could measure the volume. And when the reaction stops, you would stop your stopwatch and you say, okay, look at that, I can measure the volume. It's 15 milliliters of gas, and it took 90 seconds to get that. So a real simple technique here to measure the rate of this chemical reaction. So you're measuring the rate of successful collisions between sodium bicarbonate and hydrochloric acid. And there we go. So that's one way of measuring that particular chemical reaction. There could be others. For instance, this is an acid here, so I could measure the pH. A little more complicated procedure because you need a pH meter. This guy here is a solid, so you can measure the disappearance of the solid. However, that's problematic here because is it the rate that the chemical reaction occurs that the solid's consumed, or is it the rate at which the sodium bicarbonate dissolves in the water? All right, so you got to watch what you're measuring there. And of course, we can look at another reaction over here. So here's another example, the reaction of iron with hydrochloric acid to produce hydrogen gas and a colored ion, iron 2 chloride. So how could we measure this reaction? Well, there's several things we could look at. Seeing iron is the only solid that's there, we could measure the change in mass of the iron. So we could measure it before the reaction, let it go for a minute, stop it, take it out, weigh it again, make sure it's dry. So we can measure the change in mass over time. We can measure the change of the pH here because hydrochloric acid is the only acid that's present. So as that disappears, the pH is going to start to rise. So you can measure the change of pH over time. Likewise, we can measure the change in the gas pressure or the gas volume. So we could do the same sort of thing with this guy. We could collect the gas and measure the change in volume over time. We could also measure the change in gas volume. We just said that. We could also measure the change of the color of solution because it's going to be colorless in the beginning. And as the reaction proceeds, it's going to get oranger and oranger and oranger. So the further and the more iron chloride that gets produced, the darker orange this is going to become. So in this particular reaction, we could use something called a colorimeter. And this is just a little schematic diagram how that works. It's a little machine. You put your sample down in the machine, and here's the orange iron chloride. And the machine would shoot some white light through it, and the orange would scatter orange light. So the orange light gets scattered, and the remaining light gets passed through and gets detected by a detector. So the darker the orange color, the more iron ions are present. Therefore, it can do a calculation for you and tell you what the concentration of the iron ion is, determined by the amount of orange that gets scattered. All right, so don't worry about that. That's just showing you a way that we can measure it. Okay. Now we can look at measuring conductivity here, but this is problematic in this particular reaction because it's going to be difficult to measure conductivity here because hydrochloric acid is going to be, acids conduct electricity because they ionize in water. The iron chloride is aqueous as well, which is going to be producing ions. So I'm having ions in the beginning in the reactant side, and I've got ions on the product side. So it's going to be very difficult to try and measure an accurate change here because it's going to be electrically conductive before, and it's going to be electrically conductive after. So probably not a good choice to be electrical conductivity as a way of measuring. It would work, but it's going to be difficult. Okay, quick Jeopardy here, a little multiple choice question. You got a brand new bottle of dill pickles. Your mouth is watering at the thought of crunching into one. The only problem is that the lid's stuck. How do you remove the lid safely? Safely is a key word here. And the idea behind that, you're going to use your science knowledge here now. You're going to run them under hot water and let the lid expand, and then you'll easily get it off. Okay? The other choices are not safe. Cold water running over the lid is going to cause the lid to get even tighter. Okay, here's another type of question, typical multiple choice question that you might get on a public exam. It says, how do the motion of the molecules in a glass of water at 15 compare with another glass at 80? And the idea behind this, of course, is the higher the temperature, the more energy it has. So therefore, the molecules should be moving faster in 80 than they would be in 50. Okay, and last but not least here, this is a type of question that might show up at the end on the constructed response item. It says, use the collision theory to explain why a container of gasoline left outside on a hot summer day does not ignite. It doesn't blow up. Why not? Well, three conditions have to be met for that, isn't it? That's the collision theory. So in this question, you would state the collision theory. Number one, are there collisions? Okay, yes, there are going to be collisions because the gasoline is in an open container. Right? So the oxygen is going to get in there and mix with the gasoline vapors. So that condition is met. Number two here, orientation. By chance, will some of these oxygen molecules collide in the correct orientation with the gasoline? Probably. If enough of them get in there, then yeah, 1 out of a billion would probably, or 2 out of a million, you know, at some point in time, one of these oxygens is going to hit in the correct orientation to cause a chemical reaction. So yeah, we're going to have orientation. You know, that's a random thing. That's a chance. You're going to get it. All right. If molecules collide, then by chance, some of them will definitely collide. If enough of them collide, then you may get enough for that. Number three here. Even though it's in the hot sun, there still may not be sufficient energy to start the chemical reaction. Even though it's warm and the oxygen is mixing with the gasoline and some of them are going to collide in the correct orientation, they still may not be colliding with enough intensity to start that chemical reaction. Now, if you had to have some kind of ignition source here, a lighter, a spark, you know, static electricity, that could be enough to give it the energy it needs. But at this particular instant, it doesn't tell us that a source of ignition is there. So it doesn't have enough intensity to cause the reaction to start. And there we go. Okay, that's the end of Unit 1, Section 1, Lesson 1.